from current slide. And, we can turn on the projector. The only announcement I know about, I know there's some more out there, I just haven't seen or printed or whatever, but our SACS team, Southern Association of Colleges and Schools, our accrediting agency, is on campus. We have a reaccreditation visit about once every 10 years. And all the paperwork has been being done for well over a year, and all the planning and all the everything else. That's why you smell fresh paint when you walk in the building. They're here. But anyway, they have to follow up with an actual site visit, and that's what's happening now. It should be basically the last stage of it. Of course, if they find any things they like to comment on, then there will be follow-up, not visits, but just getting back, telling we corrected what they found or whatever. But basically, this should be about it, that we should be through with it sometime today or tomorrow. They were on this campus yesterday, I heard. I never saw them. And then they've been on the Birmingham campus just about all today. And they were having a luncheon, but I wasn't invited. But someone stopped me in the hall to find out what he needed to talk about if they quizzed him on anything. So I gave him the best information I could think of. And then so hopefully it'll be over with soon. And I think it's gone nicely as far as I know. There's no issues. But if there are, we'll hear about them. But we hopefully will be through with this very soon. But anyway, if things have been seemed a little crazy, they are. Okay, and that's what they've been crazy about. All right, now, my memory is we were just going through 13.9 and 13.10, just slideshow, showing you applications of Extrema. And any questions on anything we've done so far or what we're doing now? So you're not responsible for this on the test, but in case you ever run into it, here's how this works. Many examples of lots of things involve mathematical models. Randomized drug testing, agricultural experiments, they're just all over the place. Physics phenomena, physical phenomena, stuff like this. But for example, here's one that's called the quadratic model for profit. Okay, frankly, I'd never heard anything phrased this way, but it's called the method of least squares. There's several ways to develop such models, and one is called the method of least squares. That's where the quadratic comes from the squares. The quadratic model for profit. Why profit? I'm not sure. In constructing a model to represent a particular phenomenon, the goals are simplicity and accuracy. Try to keep it as simple as possible, but try to get it as accurate as possible. When you're dealing with data, with information that you've collected from somewhere, there's always variations. There's always stuff all over the place. So what you try for is find a model as simple as you can make it that comes pretty close to being as accurate as you can. So, of course, these goals are often in conflict with each other. The simpler you get it, you lose accuracy. The more accurate you get it so complicated you can't work with it. So that's what we mean by the conflict there. For instance, a simple linear model for the points shown here, I wish they had just left off the line to begin with and just plotted the points. Okay? And if you just see that, what they call scatter here, then you try to estimate what will be the best line that fits those data. A simple linear model for these points is y is equal to 1.9x minus 5. Now, I'm not even sure I find that. If you extend this line down this way, it looks like it's not as far as 5 units. So I'm not sure that's quite an accurate model, but we'll just give them the benefit of the doubt. Now, when I'm looking at this, I say this one misses by a fair amount here. This one misses by just about the same amount there. That one misses a little bit here. That one misses even less there. I would say this is a pretty good model. I wouldn't necessarily think it was going to be the best, but maybe it is. Okay? That may be the best fit that you can get to these data. Now, your tendency is to look this way, and that would be a pretty good way to do it. You see you're off here and here about just about the same amount. This a little bit more, but this one again is a little bit less. That one's not quite on, but it's awfully close. So again, this doesn't actually to me look like a perfect, the very best model, but it's a pretty good one. Okay? These points down here, not too good. These points up here, a little bit better. Okay? Now, however, figure 1375, this one we just looked at, shows that by choosing a slightly more complicated quadratic model, this one, you can achieve even greater accuracy. Oh, yes, look at this. Off by just a little there, a tiny amount there, almost on the money there, just a little off there, a hair off there. Quadratic map model matches the data so much more completely. Okay? And you can keep increasing the degree of the polynomial. Once you get up to 1, 2, 3, 4, 5, a fifth degree polynomial, you can go through every point right on the nose. Okay? That's the nature of it. But that's going to be a weird looking thing. It's not going to be simple. Okay? It'll give you great accuracy, but it won't be very simple. Now, in real life, what you're trying to do is get the models that have some physical meaning as well. And if you knew of only one variation that could be causing this, a linear model is probably going to be your best bet. But if you know there are going to be perhaps 2 or more things, then perhaps a quadratic would be a better thing because you have more sources of the variation. And this certainly seems to clean up things down here. However, usually when you have small numbers like this, that's not far from, it's pretty close to 2 here, 1 there, it looks like. 5, what is that? Oh, they guess 2, 1, 5, 2, so 6, okay. Seldom do you have data that clean. I mean, most of the time it's going to be decimals and fractions and stuff. These are falling right on the hatch mark, so this is sort of a made-up problem anyway. But indeed here, I think your quadratic model probably would be best. Okay? A measure of how well the model, y is equal to f of x, fits the collection of points, x of 1, y1, x of 2, y of 2, x of 3, y of 3, all the way up to x of n, y of n. You can add the squares of the differences between the actual y values and the values given by the model to obtain the sum of the squared errors. Okay? So what you're looking at, the difference between what your prediction was and what your actual measurement was. Now, what's going on here, squaring does 2 things for you. You could have a model if you didn't do the square here, you could have a model that's way off here and way off here, and those two way off completely cancel each other out, because this is a minus error and that's a plus error, or something like that. And you would have, oh, that's a great model, and yet it didn't go through either one of them even close to it. But you could get it. By doing the squares, okay, number one, you can't have any negatives, so you're not subtracting off something. So you're minimizing the squared values. That's what we're ultimately getting at, okay? So that's one of the reasons to do that. And then almost seems like you could do absolute value of it as well, but those are weird functions to deal with. This is much, I think, easier to fiddle with, okay? But this is what you're measuring with the sum of the squared errors would be this. That's why, if you noticed,
well, are you going to each point on the line and say, let me subtract the difference from each one?
Yeah, and that's why when I did this, the first time I did this way, because that's actually what you're doing. Here is the actual value, there's your projected value. So it's that distance squared, this distance squared, not the closest point squared. That's what always your tendency is, but it's the predicted minus actual squared, predicted minus actual squared, predicted minus actual squared. That would be awfully close, predicted minus actual squared, predicted minus actual squared. It doesn't matter which one you put first, because you're going to square the difference anyway. So that's why it's also what I was sort of indicating. Well, it's getting into something else. I don't want to muddy the water with that yet. Okay. Now, graphically, S can be interpreted as the sum of the squares of the vertical distances, that's what I was saying, between the graph of F and the given points in the plane. So it's that distance, not the closest distance, that distance squared plus that distance squared plus that distance squared. Minimize, you square each of those and you're trying to minimize that summation is what ultimately we're getting to. Okay, if the model is perfect, then that sum will be zero, because that would be on the line, that would be on the line, that would be on the line. They'd have to be in order to get it to be zero, because anything off the line, when you square it, it's not going to be zero, ever. You're adding them up, so they get further from zero. However, when perfection is not feasible, you're dealing with real data, usually it's not, you can settle for a model that minimizes the S. And that's the whole purpose of extreme. As soon as you see the word minimize, that opens the door for our extreme measures. Okay?
Well, you got, if the sum of S is equal to zero, but you go back to what you said before, you can have one way off here and one way off here, and they cancel each other out.
Well, that would be if you didn't square the difference. By squaring the difference, you guarantee you're always going to count that difference. Okay, because they're always positive, so you're minimizing a positive number. The only way that would be if these were dead on the line. If you're just doing the difference, yeah, you could get these two to be way off and that one even further off, and if they added up to zero, you say, hey, perfect fit. Nowhere close. Okay, but when you're doing the square of those distances, no. Okay. And that's what your S is. It's the square of D1, D2, D3. Add it together. Adding positive numbers, you can make them more positive. Okay. So for instance, the sum of the squared errors for the linear model in figure, this one here, 1374, S is equal to 17.6. Oh, this is the one we had to begin with. Because the distance here looks like at least 2. So 2 squared would be 4. This one, I think, would be at least, well, it may be 3. That would be 9 plus 4 is 13. Yeah, I can easily see where this could add up to be something in the order of 17. Even that distance there is going to be when you square it. That difference there squared is not going to be very much at all. Now, statisticians call the linear model that minimizes the sum of those squares, sum of the square of the errors, is the least squares regression line. The proof that this line actually minimizes S involves the minimizing of a function of two variables, which is exactly what we've been doing in this chapter. Okay. Okay. So here's theorem 1318, which is on top of page 951. The least squares regression line for this data set here, x, y, x1, y1, x2, y2, x3, y3, all up to x sub n, y sub n. Finite. They're always finite. These are not infinite. Okay? Is given by f of x is equal to ax plus b. That's your equation for a line. Any old line. Okay. Now, the least square regression line is given by a sorry. All right. They just pop this in there on you, and without a whole lot of backup here. This is the problem with most things dealing with statistics. It just gives you big old hairy formulas without a real good, clear indication of how they get them. There's certainly some way you got them, but they don't give them to you. And I hate memorizing equations. I want to see how they derived it. I'm trying right now to see that. Since we're not responsible for this, I'm just going to let it go. That's what it is. Okay? Notice here is the product of xi, yi, which is a weird thing to... There's a sense you wouldn't be expecting that. And you're subtracting from the sum of those products n times the sum of the products, because you got n of them. Okay? Subtracting from it the sum of the x of i's and multiplied by the y sub i's. That's your numerator. Your denominator is n times this thing squared minus this. Now, this is beginning to look a little more reasonable. Well, just a little bit. This is the sum of the squares of your x values. This is the sum of the x values squared, so no, it's not really doing. This one multiplied by n, that one's not. So I'm sure there is a fairly clear way of achieving this. Well, not clear, but reasonable way of doing it, but it probably take multiple steps. The b over here would be the notice the a's are dealing mostly with the x's. Yeah, there's y's in there, but the denominator is all x's. The b's, on the other hand, are more related to your y's. Yeah, there's x's in here too, but it leads off with the y's and then subtracts off. They stuck this one in on you. This a is this thing here, goes in front of that. So it really is a mess. This would almost make it look like, well, let's just calculate that b first. No, you got to calculate the a first to plug that in here. And the bottom line of this, you don't do this by hand most of the time. This is done by a computer. You can program the computer to do all these calculations for you. Then plug that in here and do those calculations. That's about the only way to go. For a very small data set, yeah, you can work them out by hand. But if you've got anything of a decent sample size, hang that up, you're going to have a computer assist. Yeah.
See if I can read it. Don't have a trouble. See.
And this.
Okay. I see. That's not a G, because I was having problems. Where's the G coming from? That's all lines.
Oh yeah, these are all eyes here. Yeah, I think so. Yeah. The eyes are counting from 1 to n. That's your data points. Okay. If the x values are symmetrically spaced about the y-axis, then the sum of your x sub i's is going to be 0. Where does that show up? Right here. Okay? And right there. Okay? And right there. Okay? The sum of the squares won't be 0, but the sum of the x sub i's will be 0 there, there, and there. That simplifies things big time, but that's really a huge simplification. The formulas for A and B then simply become, again, if you wipe out these two terms, the sum of this, oh, the ends cancel out then. Okay? And that becomes the A. That's what you plug in here. Oh, but that's disappeared. That's just some of the y's there. So let's see. Yeah, that's exactly what. What's that?
Well, the first one that the end cancel out, we've got the sum x, y, and then just leave it with y over there in front.
You mean?
Here, we've got, oh, that's an x squared.
Yeah, that's an x squared. Yeah, and you can't divide, you can't cancel out things within a sum. That's exactly like you would expect. No more A dependence on that. Okay. That simplification is often possible with a translation from the x values. So let's say you did have, let's use the graph here. You have something that's happening like this, fairly symmetric. Then rather than using x, use x minus whatever your midpoint value is here. Then basically that's like you're moving your axis over here, and then you can use this kind of simplification. That's a translation of the x values. For instance, given that the x values in the data collection consist of these 9, 10, 11, 12, and 13, you can let 11 be represented by 0, and this will be -1, -2, +1, and +2. Now, you're able to do this. That really cleans up the stuff. Notice what I sort of arm waved over there. The y's don't have to be symmetric, it's just the x's. If the x values are symmetrically spaced about the y-axis, or about some axis of symmetry, you can do this. Just called the change of variables. Okay? Now, we're not going to do the examples, but to find the least squares regression line for the points. Here we have -3, -1, 0, 2. Well, midpoint here would be about -1/2, wouldn't it? This would be -1/2 off here, and that's -2.5 there. This would be 1/2 off here, 2.5 off there. So if you start off that way, then because these are evenly spaced, you can do that. Okay? Table shows the calculations involving finding the least square regression line for n = 4. No, they're just going to take it directly as it said. Good. Okay. They're not translating. See, well, maybe they will in a minute. Okay, so anyway, that comes up. That's a fairly easy thing to do. And remember, this showed up here, here, and there. Okay, so that's one that you need to calculate. The xi, xy, that's here. X squared is there, y is there, and there. So really, the individual summations you need are 1, 2, 3, 4. You already counted that one. Whoa, where did you go? Now, I didn't do a thing. Punching the board shouldn't do anything. Okay. My thought on this, I think this plug, after a while, starts having variations of that. My power light is flickering. This thing's flickering. Should try plugging it in under there. Anyway. So you have 1 summation, 2 summations, 3 summations, 4 summations. This one's already counted, this one's already counted, and that one's already counted. So 4 summations, here they are. The first one is the summation of the x sub i's, y sub i's, x sub I times y sub I, and x sub I squared. Okay? So here's your summation of the x sub I. You just add them up. Minus 4 plus 2 is minus 2. Y sub i's, add those up, 6. X y's, product, you have to do this. Minus 1, 0, or I'm sorry, 0, minus 1, and 6. That's all you got. Add those up, you get 5. And then the x sub I squared, that would be 9, and 1 is 10, and 4 is 14. There you go. With small data sets, yes, you can do this. Okay? So that gives you the data you need there. Your n is 4. Okay. So your A term would be 4 times that product there, which was 5. That would be 20 up there, minus the product of your summations of x's and y's. That would be 12. So 20 plus 12 is 32. Divided by 4 times 14, boy, that's getting a big number. What's that, 52? Minus, I'm sorry.
4 times 14.
Yeah, 56, sorry. 56. And then your x sub I squared. That would be 4, so 52. Okay, that would be 4 times 5 minus 2 times 6, so that would be 20 plus 12 is 32. 56 minus 4. Okay, it comes out 8/13. All right, that's your slope of those points. The A is your slope figure. Now your B, let's go back to the formula, is 1 over n times the summation of the y's minus a times the summation of the x. And the 1 over n's times them all. So, oops, yeah. Summation of, I'm just going to let them do it because I can't carry all those numbers in my brain when I flick through like this. So there it is. It's 1 over 4. That summation of the y's was 6. And it was A, which is 8/13 times summation of the x's, which was -2. So let's see what we got. 6 minus 8/13 times -2, that would be plus 16/13. Whatever that comes up to, and divide by 4. It'll be a messy fraction. 1/4 of 6 minus 18/13 times -2, 47/26. One of my favorite numbers of all time. Okay. That's your B. So, drawing that in there, y-intercept is almost 2, not quite. 52/26 would have been 2. So you're pretty close there. You really look right on the money here. Just off a little here, a little there, and not far off there at all. That's a pretty decent regression line. Of course, you only got 4 points, okay? And they're in a fairly quasi-linear relationship. So, yeah. That's doable. Okay, I'm spending more time on this than really what I had planned. Oh, but that's it. That's example 3. That's all she wrote for here. Okay. I was kind of expecting a few more examples. Then that's what we got. Okay. So let's end this. Again, you're not responsible for that, but that's how you go about doing it. Let's move to 1310. And I did give you all your tests last time, didn't you? Okay, good. 1310 is Lagrange multipliers. And again, this is something really big for optimization purposes. And that's where you would use these. We really need to move because we've got another chapter to go. Functions of several variables, Lagrange multiplier, 1310, the last section in here. They say our objective is to understand the method of Lagrange multipliers, use Lagrange multipliers to solve constrained optimization problems, and then use method of Lagrange multipliers with 2 constraints. Okay. So many optimization problems have restrictions or constraints on the values that can be used to produce the optimal solution. Such constraints tend to complicate optimization problems because the optimal solution can occur at a boundary point of the domain. Now that sounds like a nice sentence, but it doesn't give you any reason why that would be an issue. In this section, you'll study an ingenious technique for solving such problems. It's called the method of Lagrange multiplier. To see how this technique works, consider the problem of finding the rectangle of maximum area that can be inscribed in the ellipse x squared over 3 squared plus y squared over 4 squared is equal to 1. Okay? Find the rectangle that can be inscribed inside that ellipse. Okay? Now, hopefully they'll show a picture. Here it is. So, what they do first, of course, is, since this is centered at the origin, thank you very much, okay, and this goes up 4 units on the y, up and down 4 units on the y, left and right 3 units on the x. So it's perfectly symmetric about the origin, okay? And then you pick a rectangle. Doesn't have to be the correct one or anything, but what you do here, your constraint is, and all you have to do is, let's deal in the first quadrant. This corner point here is going to be the point xy. Now, of course, you're constrained. It can't be any, y has to be less than or equal to 4, and x has to be less than or equal to, in fact, less than 4 and less than 3. If it's equal to it, you're not going to have a bunch of rectangles. So less than that. So now, okay. They start out saying this when we haven't gotten to it yet, what they call the objective function, f of xy is equal to 4xy. Now that's not completely clear where that came from yet. Okay? So let's move on and maybe that will become so. They haven't even told us what they mean by objective function. Okay, but there's a setup. Now all you have to do, and what it is, find the what we're looking for is the maximum, consider a problem from the rectangle of maximum area that can be inscribed in that ellipse. So if you can find the one maximum rectangle in the first quadrant here, then you're going to multiply by 4. So the maximum rectangle here is going to produce the maximum rectangle there. So you don't have to do the whole thing, but let's just at least do that. Okay? So pick a point xy. X is between 0 and 3, and y is between 0 and 4. Okay? Can't be 0, can't be 3, can't be 4. Okay. The area is then going to be x times y. That would be this area right here. 4xy would be 4 times y. So that's what the 4xy. That's the objective function there. F of xy is 4xy. That is what you're looking for. You're trying to maximize that function. Okay? Now, because the rectangle has side of lengths 2x and 2y, its area is given by f of xy is equal to 4xy. That's where they got that. Okay? You want to find x and y such that f of xy is a maximum. Okay? Your choice of xy is restricted to the first quadrant points that lie on the ellipse x squared plus over 3 squared plus y squared over 4 squared is equal to 1. Okay? Now consider the constraint equation to be the fixed level curve where your g of xy, and I have to throw in another variable name here, is equal to that. Okay? The level curves of f represent a family of hyperbolas such that the f of xy is equal to 4xy, but that needs to be a constant. So wherever that area is, that's going to be a constant for the effect. In that family, the level curves that meet the constraint, which is up there, that's the constraint equation, corresponds to hyperbolas that intersect the ellipse. Moreover, to maximize, this is a lot of verbiage here, maximize the f of xy, which is this one, you want to find the hyperbola that just barely satisfies the constraint. That's that up there. Now, a lot of blah, blah, blah. Okay? The level curves that does this is the one that is tangent to the ellipse. Okay? Now, these are the level curves for this function here. Okay? And the one that is tangent to the ellipse. These are all level curves for this, but they don't even touch the ellipse. We want the one that touches right there, because that's going to give you your maximum area here. Okay? The constraint is it has to touch that parabola. I mean that ellipse. They list this as being k is equal to 24. Now, they haven't shown you or told you how they arrived at that. So maybe that's coming up now. To find the appropriate hyperbola, use the fact that two curves are tangent at a point if and only if their gradients are parallel. The gradients are parallel there. This means that the gradient of f of xy must be a scalar multiple of the gradient of g of xy at the point of tangency. Now we're getting to where we actually use the calculus we did in the first part of the chapter. In the context of constrained optimization problems, the scalar is denoted by lambda, and that's going to be delta f is equal to lambda times gradient of f is equal to lambda times gradient of g. Okay? So, gradient of f is equal to lambda times gradient of g. The scalar lambda is called the Lagrange multiplier. The theorem 1319 right here gives the necessary conditions for the existence of such multiplier. If f and g must have continuous first partial derivatives. Obviously, you can't take the gradient if they don't. Continuous first partial derivatives such that f has an extremum at the point x0, y0 on the smooth constraint curve g of x is equal, g of xy is equal to c. And that c is not your lambda, that's just that's someplace where this g of xy is a constant. Now, if the gradient of g of x0, y0, that's that point there, is not equal to 0, then there is a real number lambda such that this gradient at x0, y0 is equal to lambda times that gradient. That's basically the condition for the operation of Lagrange theorem. Now, the method that we employ then, let f and g satisfy the hypotheses of Lagrange's theorem, let f have minimum or maximum, have a minimum or maximum subject to the constraint that g of xy is equal to c. To find the minimum or maximum of f, use these steps. Okay. Simultaneously, solve the equations gradient of f of xy is equal to lambda times the gradient of g of xy, and g of xy is equal to c by solving the following systems of equations. Okay? Gradient of f is partial of f with respect to x, partial of f with respect to x at xy is equal to lambda times the partial of g with respect to x at xy. Okay? Partial of f with respect to y at xy is equal to lambda times partial of g with respect to y at xy. And then this last one is just that g of xy is a constant. Evaluate f at each solution point obtained in this step. Okay? There may be multiple. So evaluate your f function there. The greatest value yields the maximum of f subject to this constraint, g of x is equal to c. The least value yields the minimum of f subject to that condition. Okay? So that's when you solve your equations and then plug in. Yeah.
Question. Item 2 there says evaluate.
Right.
And then you have function g of xy is equal to c. You have a maximum. You have g of xy is equal to c. You're going to have a minimum. What's the test to tell which one is which? What's the test?
Okay. It's the value of the f. If f is
Greater.
Yeah, greater than
0.
Yeah, right.
Less than 0.
Or they can. The maximum value for this f will then be the maximum of f subject to that constraint. The minimum that you would get from of f. It could be. Okay. just for fun, we'll make the F the Y value and the G the X value. If it's here, they both positive. Here one positive, negative. Here one positive and one negative. Here both negative. So it just max in there. Max F, min F. Okay. Greatest, yes. So it don't have to be plus or minus.
It's just the greatest number.
Greatest, of the values that you got. You have just solution points here. Probably 3. Evaluate F at all 3 of those points. The maximum F is the max, minimum F. The other one, don't even know why it's in there. Okay? But it's not a max or a min. It may be a place where it does something like that, or something sort of weird like that. Okay. Now, constrained optimization problems. Find the maximum value of the one we had before, f of xy is equal to 4xy, where x has to be greater than 0. Areas don't make any sense if it wasn't. Okay? And y has to be greater than 0. Doesn't make any sense if it's not. I mean, yeah, on the graph, it could be down there, but we're dealing with first quadrant, so that keeps us in first quadrant. Subject to the constraint that you have to equal that. Okay? So this is your g function. This is your f function. Now I haven't quite. The g function is this one. Now, there's your constant. This is your g of x. There's your constant 1. Okay? So g of x equal 1. G of x equal 1. So, here's your f, there's your g. First thing you do, take your gradient. Gradient of f is, I wasn't going to do these, but let's just do them quickly. 4y, 4yi, that's your f sub x. And 4xj, that would be your f sub j, okay? F sub y, okay? So you got those two. And then we have, this is partial of this with respect to x would be 2/9 x, and this would be 2/16 y, okay? So, this is 4y I plus 4xj, and then the lambda goes with this one, and that would be 2/9 x and 2 lambda x ninths, however you want to say that. And this would just be 2, and that would be 16, so that comes up 1/8 lambda x, lambda y there. So there's your system of equations. Now the first one is 4y is equal to 2/9 lambda x. Second equation would be 4x is equal to lambda hy. Okay, I didn't write this one down. The third equation is that. Okay. Oh, here's the second one. 4x here is equal to 1/8 lambda y here. Okay, and your third equation is just simply that. That's your constant constraint. Constraint. All right. Now, what you do here is basically solve both of these for lambda. Right. I'm going to find out what lambda is, not solve it for lambda. divided this by 4, and you have 1/18 x. 1/18 lambda x. Y is equal to 1/18 lambda x. If you plug that in here, then solve for that. Yeah, that's what they did. 4x. Yes. They did it the other way. Anyway, this gives you, if you multiply both sides by x here divided by 8. I don't know why they even wrote it like this. I was 9/4 divided by 4. 9/16 y squared. So x squared is equal to 9/16 y squared. That's from the first two equations. Your next equation is that one. So if you plug in this for your x squared up there, your 9's going to go away pretty quickly. Let's them do the work for me. Substituting that value for x squared in the constraint equation, third equation, you get y squared is equal to 8, so y is plus or minus 2√2. Now, you come up with two solutions, plus or minus 2√2. Now, plug those into your original f, okay, because y is greater than 0, choose the positive value, and find that x squared is equal to 9/16 y squared. We already had that, okay, and put the y value of 8. Y squared is equal to 8. So that would give you 9/2. That was what x squared would be. That would be 3/√2. Plus or minus 3/√2. But again, we're only doing positive x's, so that would be 3/√2. So your y is 2√2, and your x is 3/√2. So the maximum value would be at that location. The x location there, the y location there, and that should give you, plug it in. Your x is, you multiply x times y, so the √2's go out. That leaves you 6. 4 times 6 is 24. So that's, goodness, they can make this difficult. 24, there we go. So that's the maximum area that you can get out of inscribing a rectangle, into that ellipse. Economists call the Lagrange multiplier obtained in a production function as the marginal productivity of money. They always have weird names. For instance, if the marginal productivity of money is lambda, and the funny thing is we never did stop to say what lambda was, okay? And x represents the units of labor, y represents the unit of capital, then the marginal productivity of money, x equals to 50 and y is equal to 50, is this goes back to the formula they came up with earlier.
I'm trying to make sense of natural terms. That means every dollar they took in.
Right.
What's lambda in this case? The marginal productivity
of money, where x represents the units of labor and y represents the units of capital. So the labor, and I can't remember exactly where it was. I think it was the beginning of the last section. What's that?
They're saying got to put in 33 cents for every additional unit of product. If you invest $0.334 in,
Right. Oh,
you
okay.
will get one more unit of product.
Yeah. Okay. Yeah. The marginal productivity of money. Yeah. For every dollar you put in, you get that much more product out of it. Is that what? Yeah. Which means that for each additional, okay, I see, spent on production, an additional 3.334, a third unit of product can be produced. So you put in another dollar, and you get a third of the product out. Okay. Why? Because part of it's going to labor, and other expenses. You only get so much product. But what are you trying to optimize? Amount of product, profit from the product, that then enters another issue.
And it said which one.
Right.
I would have thought that you said you will optimize the product.
Right.
Then how much of the dollar.
Yeah. And yeah, I think that's what when they say marginal productivity of money, what is going to be the maximum, I guess, is it, return that you get. That would be okay. All right. What if you had two constraints? For the optimization problem involving two constraint functions, G and H, you can introduce a second Lagrange multiplier, mu. Why not? Okay? And you have lambda, mu, L, and M. Okay? Then solve this equation. This is your function you're trying to optimize is equal to lambda G, then the gradient of G plus mu times the gradient of H. Where the gradient vectors are not parallel as illustrated in example 5. If they're parallel, you could just write it as one equation. So here's your T. The temperature at each point on the sphere will be 20 plus 2x plus 2y plus z squared. Temperature at each point on the sphere. The sphere is a strange number. X squared plus y squared plus z squared is equal to 11. Why 11? I don't know. Okay. So your R would be square root of 11. Find the extreme temperatures on the curve formed by intersection of the plane x plus y plus z equals 3 and the sphere. Extreme temperatures on the curve formed by this. So the first constraint, you've got to be on the sphere. The second constraint, you've got to be on the plane where it intersects the sphere. Okay? And you're trying to optimize or find the extreme temperature, the max and the min on that setup. Okay? Now, two constraints are your G of X was this one, and your H of X was this one. Okay. Now, your T of X, the actual, what did they call that before? Wasn't target function. What did they call it? Objective function. Objective function. Target objective. Okay. All right. So if you do the gradient of the objective function, that was 2i, 2j, 2zk. Now this is 2x, 2y, and z squared. Okay? What's z squared? Your lambda times your gradient here, this was the sphere, okay? That would be 2 lambda x plus 2 lambda y plus 2 lambda z. And then your plane, this would just be mu, 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 okay? Because it was x plus y plus z. You can write the the following system of equations, okay? The first one is 2 from the objective function is equal to 2 lambda x plus mu. Second one would be 2 is equal to 2 lambda y plus mu. And the third one would be 2z is equal to 2 lambda z plus mu. Okay? And then your fourth equation, okay, would be, you got fourth and fifth, was g was equal to 11 and h was equal to 1, I believe it was, wasn't it? I don't remember now. Here's your second one. 2 is equal to 2 lambda y plus mu. The third is 2z is equal to 2 lambda z plus mu. Now, your fourth equation was your first constraint, square plus y squared z squared is equal to 11. And your second one, this is what I couldn't remember, is 3. X and y is equal to 3. Okay. 5 equations and 1, 2, 3, 4, 5 unknowns. X squared, y, and lambda. Okay. Now, how to proceed here?
What we're going to call G.
What's that?
Which of those three up there we're going to call G?
G was this one. H was this one. G was it had to be on the sphere. H had to be on the plane.
But don't we want to take the partial of the G and then look at lambda times?
Yeah, that's what they do right here. Take the partial G, which is 2xi plus 2yj plus 2zk. Take the partial of that. Okay? And then multiply lambda times, and we got that. Take the partial of h is x. That would be I plus j plus k. Multiply mu by that, you get ui plus mu j. Now, I hope I'm not doing something stupid here, but it sure looks like to me that x is equal to y. Everything's symmetric on the sphere, everything's somewhat symmetric on the plane, but you know, they're related similarly on the plane, so it looks like to me x is equal to y from this. Okay? I don't know if you want to get that, but it seems like that pops out right there. So let's see where they go. Okay? By subtracting the second equation from the first, you can look to obtain the following system. Lambda is equal, lambda times x minus y is equal to 0. That concludes, sorry. All right. Now, we got that first one. I see that one. Let's go back and see how they got that second one. Okay, let me see what the second one is again. 2z minus u is equal to 0. Okay, I'm not going to just changing slides all the time. It's driving me nuts. 2z plus 1 minus lambda minus mu is equal to 0. I'm just going to take the word for it. I'm sure you can work it out. I just am not doing the work right now. So I'm showing. Anyway, you get this. So here we have an equation with 3 of our variables. Here we have an equation with 3, but these are different 3. The lambda is the same, and that's all. Okay. The x, y in the first, z, mu in the second. Then your constraint is that and that. Okay? Now, you're down to 4 equations, but like I said, you can eliminate the lambda from the first 2. You know, actually, from the first equation, you can conclude lambda is equal to 0 or x equal y. Now, I don't think lambda equals 0 is consistent with what you're doing. So I think you have to assume x is equal to y, which is what I did earlier. If lambda equals 0, you can show that the critical points are those. So they are allowing lambda to be 0. For lambda not equal 0, then x equal y, you can show that critical points occur when x equal y equal those values. 3 plus or minus 2 root 3 over 3. Okay. Finally, to find the optimal solutions, compare the temperatures at the 4 critical points. Okay. Okay. I'm having trouble seeing how they got that last thing. Okay, perhaps what they did was multiply. Oh, okay. I was going to say, where did they come up with those two equations? I mean, the variables for the function there. But anyway, they came up with a temperature of about 30.33. 30.33. All right. All right, that was it. Wow. We just don't have time to go over all these. Okay. Okay. That's enough. All right. We're going. Wait. We will end this. That was just supposed to be a slideshow. It turned out way more than I was anticipating. How are we doing on time? We have about 50, no, we have quite a bit of time left. Let's get started in chapter 14. That's a lot more. You don't have to do homework exercises in those unless you want to. There's review exercises you might find helpful for some of the test questions because CalcChat.com has tutorial help and worked out solution for the odd number exercises. So if you see some on the tests that are similar to some of these, you can go to that source there. There's a problem-solving postscript, I guess you would call it. Maybe that just stands for problem solving. But Heron's formula, which we probably had back in trig sometime in the long distant past, that what's that? Yeah, Heron's, at one time it was called Hero's formula. I think they realized they were mispronouncing or misrepresenting it. It's the one that if you have any old triangle, you know the lengths of the three sides, add them up and take half of that, and that's your semi-perimeter, and use that formula, square root of s times s minus a times s minus b times s minus c, and you get the area of that triangle. Without needing to know an angle, without needing to know where a perpendicular line is, no height is required, just the three lengths. I'm sorry. And of course you calculate the semi-perimeter from the three lengths. All right, let's start on multiple integration. Okay. Chapter 14 is multiple integration, which kind of feels like it's the reverse thing of what we were doing with partial derivatives. It's not quite. Partial derivatives is taking derivative with more than one independent variable, and integration is integrating with more than one independent variable. But you really don't use any partials when you're doing this, or otherwise. You just... I may have to stop and just get some water. Do you mind? All right. Sorry about the interruption. Here we're back. Chapter 14 is multiple integration, and 14.1 is talking about iterated, strange word, integrals, and area in the plane. Okay. We will first probably have to figure out what an iterated integral is, and then know how to evaluate one. Didn't get much better, did it? Then we'll use an iterated integral to find the area of a planar region. Okay, so what in the world are iterated integrals? All right, they have some verbiage at the top they didn't put in the slide set. This should remind you a little bit of some of what we've done in differential equations. We have done some things somewhat similar to this, especially when we did the exact equations, when we were doing, figuring out what was happening there. I think I will try to I'll back up one and start writing here. Okay? Let's just say that you know a partial derivative. Let me get my pen set up. Okay. You happen to know, for some reason, the f sub x of function of two independent variables, xy, is equal to 2xy. Oh, talk about a 10 o'clock scholar. Okay. Glad you can make it. We just finished chapter 13, which is just supposed to be a slideshow, so you weren't responsible for it on the test anyway, so you didn't miss much there. And Bill will attest to that. You missed a lot of coughing, but that was about all. No, probably somewhere. All right, so we know this. This is the beginning of 14 here. Multiple integration. What if we're doing the reverse? You can integrate functions of several variables by a similar procedure to what we did by taking derivatives, partial derivatives. So what if we knew this partial derivative was that? Okay? Now, by considering y a constant, okay, because to take the partial with respect to x, that's what you do. Consider y a constant. You can integrate with respect to x, okay? Now, if you think about what this stands for partial of f with respect to x, and the function f here is a function of x and y. So the partial will be a function of x and y as well, is equal to 2xy. Okay? Now, sort of similar to what we did before, they just do it. Okay? If you think of, most mathematicians would cringe, multiplying both sides by dx or wiggly dx, what did you call it? Crooked dx? Curly dx, okay. But just make it a dx then. That wipes it out here, and if you integrate both sides, the integral of a curly d is just like the integral of a d, you just get f of xy. Now, you're only integrating with respect to x. There's the only variable. You treat the y like a constant, just like you treated it in partial derivatives. So this would then be what? Say again? X squared y. Perfect. Plus some constant. Okay? Now, that constant, though, now this is where I said, reminds you of what we were doing in when we're doing our exact equations. This constant, because you're integrating with respect to x, this may have a y component to it, because the x isn't going to do anything to the y. You're treating y like a constant. So this constant is now no longer a constant. It's a constant function of y, or a function of y alone. Okay. Now, so that gives you your answer. Why they took so many steps, I don't know. Okay? The constant of integration, c of y, is a function of y alone. No x's in it. In other words, by integrating with respect to x, you're able to recover an f of xy only partially. The total recovery of the function of f xy from its partial derivatives is a topic we'll get in chapter 15 if we get there. Doesn't look likely now. Okay. Now, having a little difficulty here seeing where this next line comes from. Was there something I missed reading? Where did they get the 2y? The next step is they say, what if this was a definite integral? I don't know where they get the 2y. Okay? But it would be a constant, because y is a constant since you're integrating with respect to x. That would be, if you had that result, you wouldn't have a plus c of y. You would have x squared y, just like you did before, but you evaluate it between 1 and 2y. Okay? But that's evaluating x. These are x equal y, 2y, x equal 1. You do this based on the variable x. So putting those in, you have 2y squared, which is 4y squared times y, would be 4y cubed minus y. And they get that. What I don't see is where in the world they popped up and found a 2y to put up there as the beginning argument. They just made it up, drew it out of thin air, but that's how they got this. Now, somehow that's supposed to make what follows next make more sense. And frankly, well, yeah, I guess I can see it a little bit. All right, so let's move on to what they showed next. This is where then they pick up. You happen to have a partial with respect to x, okay? You're integrating that between two functions that only depend on y. And that's legal because this partial and this thing, the y is treated as a constant here. This x is your variable here, here, and here, everywhere. Y is treated as a constant, so you can evaluate it between these two constant values of some other function h, h2 of y, h1 of y. This antiderivative of this will be alpha of xy, whatever that was, okay? Because this is partial of alpha with respect to x. With respect to x's go out, and that just leaves you f, okay? The integral does the partial, the d there. You evaluate that between these two, and then that would be alpha of h2, comma y, minus alpha of h1, comma y. That's with respect to x. Now, what if you happen to have a partial with respect to y? You knew that was it. You could take the integral of that with respect to y, but then your limits of integration would be functions of x, potentially be functions of x. So, again, this is partial of f with respect to y. With respect to y, those sort of cancel out. You can think of it that way. Then the integral of a derivative is just a function. Okay? So, you wind up with f of xy evaluated. The y is evaluated between g2 of x and g1 of x. Okay? So that'd be f of x, g2 of x, minus f of x, g1 of x. With respect to y. Note that the variable of integration cannot appear in either limit of integration. The x can't show up here. Remember back with our fundamental theorem of calculus, when we did put an x up here, we had to change that to a t. And it always seems strange, but you just can't have it there. Okay? This is just a dummy variable anyway, so it just can't be there. So it makes no sense to write the integral from 0 to x of y dx. No, you're integrating out your x's, you can't throw them back in at random. In fact, that just doesn't make any sense at all. Okay. Now, ready for example 1. Evaluate this. Okay, it's legal because the d is y here. Here's your x up here. So that's going to be okay. So how would we evaluate this? First do the antiderivative with respect to y. xy squared plus y cubed. Perfect. Evaluated between 1 and x. Exactly. Okay? And what would that be? And these are y's here. This is what you substitute in for the y, the variable of integration. X cubed plus x cubed. That's 2x cubed minus minus 1. Okay? So this would be 2x cubed minus x minus 1. See how they did? Oh, good. They got it right. Good for them. Okay. Does that make sense? All right. Let's watch them do it. I could have done it horizontally. I'd like to be doing something horizontally right now. And consider x to be the constant, integrating with respect to y, exactly like we got. Evaluate it there, and that would be 2x cubed, 2x cubed. Combine those immediately, didn't they? Minus an x plus 1. Sure you got that, but it's not very obviously how they did that, but I see. Yes. Minus, here, x plus 1. They just plugged in 1. Yeah, that makes sense. Okay? Which of them be 2x cubed minus 1? All right, makes sense? Okay, what about 5 more minutes? Let's look at example 2. Now we're going to do the integral of an integral. I don't know what your gut reaction to that is, but mine would be start on the inside and work your way out. So hopefully that's how you're thinking too. So don't worry at all about the 1 to 2 here or the dx here. Don't worry about them at all. Just focus on this one. Say again?
That's the one we just did.
It's the one we just did. And what did that come out being?
2x cubed minus x minus 1.
Perfect. Okay? So now we can integrate that, and what do we get?
16 minus...
Say that again.
It's going to be 16 minus 2 minus 1.
Ooh.
Oh, wait, I'm sorry.
Integrate it first, yeah.
I was just plugging in numbers.
Yeah, okay.
Sorry.
You're chugging and plugging and chugging rather than chugging and plugging. Okay.
Yes. X to the 4th over 2.
Yep.
Minus x squared over 2 minus x.
Evaluate it from 1 to 2, which would be 16 over 2, 8, minus 2, minus 2, plus 1, isn't it? Right? All right. So, these work out nicely. Got rid of your fractions. And you have 9 minus 4 is 5. Oh, yes, that's what they got. Okay. Now, this is what they mean by an iterated integral. That example there, take off the box I drew. Oh, wait, let me take off everything I did so you can watch them do it. Okay. Using the result of example 1, just like you did, you do the integral from 1 to 2 of 2x cubed minus x minus 1 dx, and that gave you that exactly like we did, which gave you that, which is exactly that. Okay. Now, this is an example of an iterated integral. All you would do to make it look more normal is remove this. You do that as if that were in place, but most of the time that's not going to show up.
Why would you have that, like, an integral inside of an integral?
Okay.
Like, application?
Yeah. Let me see if I can think of a reasonable example. Okay. Yeah. We're going to get to it in just a few minutes.
Oh, okay.
Well, yeah, but we're not going to get to it today. What if you had trying to find the area between two functions here, okay, and going from here to here. So here's a f of y, here's a g of y. So you do strips like this, integrate f minus g, because that's the length of that, times your dy, and then do your dx's, something like that. So that's one example. When you have an odd-shaped region and you are trying to find the area in it, it may be the only way you can do it. Okay. There are others too we probably will get to as well, but not today.
I guess and it has multiple variables too.
What's that?
If it has multiple variables too, I guess.
Right. Yes, exactly. So we barely got started on 14.1, but did we get enough for you to do a few homework exercises? Hopefully so, since it was just a slideshow before. So let's see what you can get to. Ooh, it's a long section. Think you can do any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. And then start working on the iterated intervals like we just did. Any of the odds 11 through 27. They're all at Calc Chat. 15's at Calc View. If any of them give you problems, hang on. We will come back and do a few more of those. Okay? So don't sweat too badly over it. Okay? Okay, I've got to shut down.